Now, for regular viewers, I think it will come as no surprise that implementing deep reinforcement learning research papers is a difficult task. Now, the reasons for this are many, quality of the papers notwithstanding. So, chief amongst those reasons is how do you design your agent in a way that maps to the algorithm quickly and efficiently? So, how can you maintain parity with what the authors wrote in terms of the algorithmic implementation, and how can you write it quickly such that you don't get scooped by some other authors? But an even bigger problem is how do you design that software in a way that scales from a single-threaded to a multi-threaded implementation? After all, one of the biggest problems in deep reinforcement learning is the rate of sample collection. This is a very data-hungry field, so how quickly you can accumulate data will in part determine how successful your algorithm is in the end. Solving both of these problems, meaning the ability to rapidly prototype algorithms, as well as the ability to do it in a way that your software can scale from a single to a multi-threaded implementation, is the chief aim of the ACME framework from Google's DeepMind team. Now, if you're a frequent viewer of the channel, you may have caught my earlier videos where I showed you how to code reinforcement learning algorithms just like DeepMind. And in those videos, we covered the installation of the framework as well as how to get up and running and implement a very, very basic deep Q learning agent in the framework. Now, I really glossed over all of the components because there's an enormous amount of complexity there. Because, spoiler alert, it's very difficult to write software in a way that is extensible for a generic reinforcement learning algorithm, as well as able to run single and multi-threaded in a way that doesn't break. So we glossed over all that complexity, and today I want to cover more of how the framework actually functions, as well as its philosophy underpinning its design. At this stage, if you've implemented many deep reinforcement learning algorithms, this sort of diagram should be rather familiar to you. The basic idea, of course, is that we have some sort of agent that interacts with an environment by passing in actions, and those interactions produce new states from the environment as well as rewards that serve as a signal to teach the agent what is good, what it should do. Now here, all of this is treated as a black box, and it really doesn't do it justice. The actor has multiple components, the environment has a lot going on under the hood, and it leaves open questions of how do we handle the return of the observations and rewards? What do we do with this exactly? Now here we have a diagram that really lays it out in a little bit more detail. We have some pseudocode here that really lays out how this plays out in the real world. So the basic idea is we're going to have some outer loop that controls basically how many number of episodes we're going to play, and then an inner loop that handles alternating between periods of taking action and periods of learning from those actions. This changes our diagram in that our actor then gets split out into a policy, which, if you don't recall, the policy is a mathematical function that maps the input states to a particular action the agent can take. It's probabilistic in nature. And then you have some method to observe those observations. And by observe, what we really mean is how do we store those observations? It's actually a fairly tricky question. But even this is a little bit abstract, right? Because we have more going on than is let on in this. So by updating the policy, what exactly does this mean? In general, obviously, the term deep reinforcement learning implies the use of deep neural networks. So in general, we're using deep neural networks to approximate that mathematical function, the policy. And so that requires that we actually update those weights of that network. So if we think about it on yet another more abstract level, we can encapsulate all the functionality we need in an agent. And that agent is comprised of many different things. So it's comprised of a data set that handles storing information and the easy and quick retrieval of that information, perhaps in some uniform sampled or in some prioritized sampled way. That information can then be passed to a learner, which handles the functionality of performing mini-batch stochastic gradient descent on that data to update the weights of the policy network. And of course, the learner has to pass data into the policy, and the method for consuming observations has to pass data into the data set. And all the while, we have interactions with the environment where the agent is receiving observations and querying the policy on what action it should take. Now, as an aside here, the policy is a bit of a tricky thing in and of itself. So we've kind of assumed in this discussion that it is a feed-forward deep neural network. But what if it is a recurrent neural network, right? Many algorithms, say R2D2 for instance, require the use of recurrent deep neural networks, and this requires that we actually maintain state from one step of the environment to the other. So that is a bit of a tricky affair as well. How do you scale that up in a way that doesn't break when you go from a single thread to a multi-threaded implementation? And that is exceptionally important for advanced algorithms where, let's be real, most of the attention, most of the hype is. And so the good news is that ACME handles all of that for us. So it treats everything as a separate module. So each of these modules comes together in a way that allows them to be totally abstract. All of the modules themselves only see input data being passed from some other arbitrary location. It doesn't know where it comes from. It doesn't matter where it comes from. It could be a function call on a single threaded machine, or it could be a remote procedure call for a node on a cluster sitting in the cloud somewhere. It really doesn't matter. It's all abstracted out in such a way that from the perspective of each individual module, it's only receiving data, and it doesn't matter how, where, or I guess it does matter why, but it doesn't matter how or where that comes from. Now, one other thing we touched on when we looked at the pseudocode for how all of this works is the idea that the agent alternates steps of taking action and then learning from that action. Now, there is an open question of, how much time should you spend doing and how much time should you spend learning from what you just did? And that is certainly the case for deep reinforcement learning agents. In something like PPO, for instance, we will perform some time horizon number of steps, 2,000 steps, 500 steps, whatever, doesn't really matter. And then we will perform mini batch stochastic gradient descent on those number of time steps. And it's a hyperparameter, the number of steps in our horizon versus the number of times we loop over the training data to perform actual gradient descent on it. So the question of how much time you spend learning versus doing is an open one and is particularly important for deep reinforcement learning agents. So this problem gets exacerbated when we're talking about distributed agents, right? Because ostensibly, the data collection is done in such a way that we simply take each agent and shuffle its data off into some data table server, and then we can query that server later on any of the individual threads. So all of the agents are uploading data to the same table, and that is queried by each individual actor in parallel. And this really leads to another issue in the distributed setting. How do you handle the problem of learning too much or doing too much? And if you rely on each individual actor to figure that out for themselves, you're going to run into some problems very, very quickly. It's not hard to see why. So since the actors are all querying the data set, it makes sense to incorporate some functionality in that data set to limit the amount of time the agent can spend in either learning or doing, such that if the agent spends too much time in one but not the other, you can actually block one activity until the other activity catches up. So if it spends too much time learning and not enough time producing data, you can tell it, hey, stop doing the learning and do more acting. And it can handle the balance between those two activities in such a way that you don't go too far in the direction of one or the other, because that is incredibly inefficient in and of itself. So that is a 30,000 foot overview of the ACME library. The basic essence of it is that we've abstracted out all of the core components of our agent: the policy, the learner, the actor, the data storage and retrieval, and the environment loop, in such a way that we can actually go from single-threaded to multi-threaded implementations without rewriting the core functionality of our agent. One thing I do want to point out, though, is that there's a bit of truth in marketing here I have to do, and that is that ACME itself is not a multi-threaded framework. It is simply the framework that allows us to build agents that can scale very easily and rapidly. The framework for handling the multi-threaded applications is called Launchpad, and that's also a Google product, or excuse me, DeepMind product, and that is just detailed in a separate paper on that particular framework, because obviously it's beyond the scope of the ACME paper. Now, if you're the kind of person that likes to implement papers on your own from scratch, you can check out the Neural Net Academy. That's my shtick. I teach students how to go from the algorithm in the paper to a functional code implementation. And then I'll even show you how the implementation we come up with oftentimes differs from what the authors actually did. Check the link in the description for that if it's something you're interested in. If not, Hit the subscribe button because that is free, and free is oftentimes the best price. Make sure to hit the bell icon as well so you get notified when I release a new video, and I'll see you in that next video.